All right, the next thing I'm going to talk about is something called the TDS equations. Now, here's the thing about the TDS equations. These are going to be a stepping stone to for things that we are going to use in this class. We're never going to really use the TDS equations as we are exploring or solving problems, but these TDS equations are what we're going to use to create the equations that we are going to be dealing with. So let's look at this. Let's look at a closed system. Okay, here's my closed system. Okay, and here is my boundary. And I'm going to say that what laws go with this? I can say that du is equal to dq, and I'm going to call this internally reversible, minus dw, internally reversible. Okay, now this is the first law, but I'm just writing it in a different way. I'm writing it in differential form. Instead of saying delta u, I'm writing it as du. And notice I'm also applying it for internally reversible situations. Okay, that's what I'm going to try to say here. And so I know that dw for internally reversible is going to be equal to p dv. Okay, we talked about this before. Work is equal to the integral of p dv. And this is another way to write it. It takes away the integral sign. Okay, and we can also say that ds is equal to dq over temperature. This is internally reversible because we're not going to have the sigma here. Okay, or that's going to go to t times ds is equal to dq, internally reversible. So here's what I'm going to do. I am going to take this equation and put it into here, and I'm going to take this equation and substitute it into here and see what I get. So I'm going to substitute, and I'm going to get that du is going to be equal to t times ds minus p times dv. So I'm going to have, okay? Or I could write it this way. Or I can write that t ds is equal to du plus p dv. Okay, and this is our first TDS equation. Okay, this is our first TDS equation. And we can write it lowercase. We can write it, say, using math here, t times ds is equal to du plus p dv. This all applies here. These here are sorry, first TDS equation. Okay, now let's use that enthalpy is equal to U plus PV. This is a definition. Enthalpy is equal to internal energy plus pressure times volume. All right, so if we can form the differential. That dH is equal to du. Now if we differentiate PV, we're going to use the chain rule. So it's going to be plus differential of PV. So we're going to have dH is equal to du plus P dV plus V dP. Okay, remember that from our days in calculus. What happens here? Look what happens. We have du plus pdv. Du plus pdv is going to equal dH minus V dP. Okay, now that's what we had up here. Look, we have up here, we have du plus pdv. Du plus pdv, and so we can write this way, this TDS equation, TDS also equals dH minus V dP. Okay, and surprising or not, this is called the second TDS equation, and we can write it also as TDS is equal to dH minus V dP. or. This is going to be our second TdS equation. Okay, there we go. There we go. So we can also do molar if we wanted to divide this in, lowercase molars. Now, we've defined these for internally reversible processes. Here's the thing. Entropy is a property. It doesn't matter the process. Enthalpy is a property. It doesn't matter the process. Volume, pressure, temperature, these are all properties. It doesn't matter what process we're dealing with. So even though we developed them for internally reversible processes, these can work for any and all processes. Okay, and so that is where we are going to exactly what we're going to do. Okay, so the first thing we're going to do is we've talked about liquid approximation. Let's talk about incompressible substances. Okay, we're going to use this equation TdS is equal to du plus P dV. Okay, now we're going to say, I want to find out what the change in entropy is. So I'm going to say ds is equal to du over temperature plus P dV over temperature. Okay. Now, we're trying to find out what the change in entropy is. Now, what do we know? We know that the change in internal energy for an incompressible substance is equal to the specific heat times the change in temperature. And it doesn't matter which specific heat we use. It could be C sub P or C sub V. It doesn't really matter, because if for incompressible substance, C sub P is equal to C sub V. So we know this, and so we can put this into our equation. We can say ds, lowercase s here, is equal to specific heat times dt all over T plus pressure times dV all over temperature. Okay. Now, remember what happens with the incompressible substance? Can't be compressed. So what is our dV? Change in specific volume. This term is all going to go to 0 because it's incompressible. And dV, the change in specific volume, is going to be 0. So now we're just down to that ds is equal to specific heat times dt all over T. Okay, what we want to do here is we want to integrate this. Integrate this from 1 to 2 and integrate this from 1 to 2. Okay, now notice that as we do this, the left-hand side of the equation is going to be pretty easy. It's going to be S2 minus S1 is going to be equal to the integral from temperature 1 to temperature 2 of specific heat over temperature times dt. And we know that specific heat does change with temperature. This here is a function of temperature. Okay, a function of. Okay, so we'd have to know something about how the specific heat changed with temperature. However, if we assumed, and this is why I'm being very picky on your homework, you've got to talk about your assumptions. I know that the problem statement sometimes says assumptions, but I want you to explicitly define what your assumptions are. Okay, so assume here that specific heat is constant over the temperature range what happens now is this specific heat can come out of the integral. And so we're going to have S2 minus S1 is equal to the specific heat times, now what's going to happen there? We're going to have the remaining integral is dt over T. What is that? What is the integral of dt over T? That's our old friend natural log. This is going to be natural log of T2 minus the natural log of T1. In our rules of logs, we can say the S2 minus S1 is equal to the specific heat times the natural log of T2 all over T1. Okay, so this here is what we're going to use for how to find the change in entropy for an incompressible substance. This is going to be for incompressible substance. It's on your equation sheet. Okay, again, we're assuming that specific heat is constant there. Note we use the TDS equations, but we came up with a completely different equation. That was a tool that we used to get here. All right, now that's where I'm going to end today. I want you to know that we have to talk about ideal gases, and we will start those ideal gases talking about them on our next lecture. And then when we do that, we will be ready to then solve all sorts of problems, all sorts of closed system problems, and then we'll be ready to start all sorts of. I'll just have to give you in 5 minutes, give you the open system second law, and then we'll be able to solve all sorts of open system second law problems. So that's where we're going, and that's what will lead us into our third test. The grading is going slower than I've been busy these last few days, and I haven't been getting to the grading as well as I should have, but I'll get to the grading, and we'll get that test back to you so that you can see where you are no later than on Monday. And I know that's a little bit later than what I hoped, and but I'm going to get that to you and do a good job so that you can see where you are. Okay, that ends it today, and I hope you have a good rest of your day and good weekend.